Welcome to Elixir Wizards, a podcast where we talk with software developers from around the world about the Elixir language and other modern web technologies. My name is Justice Epen, and I'm your host today, a developer at SmartLogic, a Baltimore-based consulting company that has been building custom web and mobile software applications since 2005. From the SmartLogic team today, I'm joined by my wonderful co-host, Mr. Eric Ostrich. Say hi, Eric.
Hello.
And our theme this third season of Smart Software, now Elixir Wizards, is working with Elixir. And today we've got an episode that is guaranteed to get on your nerves because we've got the legendary, the luminaries, Frank Hunleth and Justin Schneck from the Nerves team. Say hi, guys. How are you doing today?
Hello.
Hello.
And this is pretty amazing because we're actually recording this the day before Justin's birthday. So happy birthday, Justin Schneck.
Yes, thank you very much.
He's turning 73.
Yep.
And I'm sorry, 37. And we're super glad to have him. And it's also Frank's daughter's birthday tomorrow. So happy birthday, Megan. Justin, how was Japan?
Oh, man. Wow. Japan was one of the most amazing experiences I think that I've ever had. Yeah. It was surreal in a way, especially because it was put up against the ElixirConf US this year, like pretty much back to back. And so it was also like the longest time that I've ever sort of traveled in one stint. It was a trip that was full of a lot of different kinds of emotion, like being away for a long period of time, being immersed in a new culture, and also just the amount of excitement and like the people in Japan being so friendly and excited about what they're working on and Elixir and Nerves in general.
Yeah. That's all cool and everything. But what were you doing there?
We had some arrangements to speak at a couple different conferences. In the earlier parts of the week, we ended up going to a meetup in Kyoto, and we ended up doing a little bit of a presentation there, getting familiar and understanding more about the needs of what's happening in the industry in Japan. And then we ended up going and traveling into Garo. It's known for its hot springs. And yes, I absolutely had the opportunity to go and participate in the Garo hot springs. What an amazing experience. But while there, we did a conference called S-West, which was about software engineering for robotics and a lot of automotive manufacturing and embedded development systems. And there was a really energized group of people there working with a lot of different kinds of technologies who were also then interested in taking the Nerves. We did like a Nerves training while we were there as well. An interesting side note, I was very much so. I do not speak Japanese, and I cannot necessarily read the kanji characters and have an understanding of a lot of it. And so I was unprepared for the fact that while working with developers who were familiar in English, and most of the people there were very good, and it was enjoyable to speak with them, but their terminals would be in the kanji character sets, and that I would be trying to debug error messages that are being presented from the system in a language that I did not understand. So I promptly made myself quite useful by playing barista to the class and brewing coffee that I brought from home for everybody. Yeah. I definitely found my place in that one. Yeah.
We actually have some kanji on our episode outline, which I cannot read. Perhaps someone else here could read that kanji.
So that's Ohayo gozaimasu.
Which has something to do with dumplings, right? What does that mean?
Good afternoon.
Okay, no dumplings involved. And Frank, how are you, sir? I've heard a bunch of words, and maybe you could tell me what they mean. What are these new EEF embedded systems, WG?
Oh, right. So this is a recent development, the Erlang Ecosystem Foundation. So that's a group that supports development and various different activities related to the Erlang and Elixir ecosystems. We recently formed a embedded systems working group. So that's to focus on building the types of systems that are built with Nerves. We're working with the GRISP team. So they have a different set of systems. So they have a very interesting piece of software used for building embedded systems, more on the Erlang side, but certainly Elixir works on it as well. So we're just getting started, and I wanted to let people know that if you're interested in embedded, especially in the industrial community, this is another resource for you to participate in to get possibly advanced industry-specific features of the Erlang Beam as it pertains to embedded systems.
I mean, we'll have a link to that on the show notes. I believe there's also something else new called VintageNet. Do you want to tell us a bit about that?
Right. So there's another piece of software library that Justin and I and quite a few others have been working on. So if you are using nerves, you've probably had to set up the network a few times. And in some cases, it works really well. In cases the existing nerves networking libraries fall short. We have a new one that's being used in production a few places, and we're working on getting it into the open source community. It's called VintageNet. Hopefully there will be a link to it. But we're currently working, and depending on when the show hits the air, it will be either posted and integrated into our documentation or on its way. Certainly, if you're looking at devices that have multi-home networks where you need to use Ethernet, Wi-Fi, need to reestablish for internet connectivity, and there are a number of other little features in there that become useful. LTE, mobile support. So that kind of stuff, you're going to be interested in looking at that library. We think it's going to be a lot easier for people to integrate on their devices.
Can you tell us about the name?
Oh, Vintage? Yeah, I think the main name means less now than it did at the first time. Then when we initially started the library, we were going all old school with some of the network implementation. And then we put a bunch of grapes on it, and it kind of stuck. So I wish I could say that there's something deep there, but no, it's kind of one of those names you picked out and kind of got used to saying.
So this isn't vintage like old. This is vintage like
well, there are some aspects of networking that we took from some pretty old implementations, but there are good ones. So it's what you want in a vintage, right?
Super duper cool. Okay, so we wanted to just touch on the Japan trip with Justin and these new libraries that you guys are pushing out there, Frank. So thank you. But the bulk of the episode, we've got a ton of questions here on performance because we thought that you guys would really have some interesting perspectives on this from your work on nerves. So Eric, do you just want to jump right into it?
Yeah, so I guess we'll start with how do you guys handle any kind of performance issues with there's at least 10 or so different devices that you all support, right? How do you work through that?
Maybe we should go back and talk about some of the devices we support because there are a lot of answers to this question. Sometimes it's easier to talk about specifics, but in general, we currently support devices that are a few hundred megahertz all the way up to multi-gigahertz. In fact, you can just run nerves on a regular PC, and some people do that. Some of the interesting devices are the low megahertz devices just because they either have some power savings that are interesting, they're sometimes lower cost, sometimes you can get by without heat sinks and fans, which can always be nice in these devices. So for the embedded side, it's important that we support some of these low ends, but then every once in a while a feature comes along where you really want to speed a device, and that's how we got into multi-core x86 devices. I think the kiosk users in particular of nerves. So these are people who are running web browsers on their devices just to get any kind of performance out of the web browser. It's kind of nice if it's a few gigahertz and a couple cores. I mean, it can go lower, but it definitely seems like there's some use for that extra capacity. So that's the breadth. Then I guess getting into handling performance, I think performance hits us in a couple areas. Some people are concerned with boot time, right? That's an interesting thing. Like you have this embedded device, you plug it in, you kind of want it to start doing whatever it's supposed to do pretty quickly. And that's a little different than, I think, a lot of other uses of Elixir and Erlang, where you're kind of looking at the device to stay on for a really long time. But if it takes us 30 seconds to boot, that's probably okay. Some embedded cases we want it to be quick. Then there's also just general performance, which I think is similar to many other fields. Possibly some things we can talk about that are quirks to the processors we run on. And I guess the third area is the performance that's more on the real-time, hard real-time. So it's not something that you normally think of Elixir and Erlang as doing as hard real-time. You want some very defined behavior for the things that you run. So let's see, I guess where should we start? You also had an interesting question about acceleration with FPGAs. So I think we can start in any of those.
So jump into it. I mean, what does that even mean?
Which the FPGA part?
All of it.
All right, well, I guess we just take it step by step. So we started at the initialization and the boot time. That one has changed. So part of getting things to boot quickly is to do the least amount of work possible. And kind of the opposite side of that is to be easy to use. If you start a few more things at the beginning, that's helpful to people. right? So if we have devices where, for example, when we first started the project on the BeagleBone, we shipped it with the Linux kernel that did practically nothing, and networking didn't come up, but that device booted very fast, and it was nice. It was kind of impressive. I mean, you could get an IEX prompt, but you couldn't do any networking. So you could argue whether that's any good or not, but it certainly was frustrating to a lot of new users not to have networking work. So we pulled in networking. And then on the Raspberry Pis, we pulled in cameras. So, we pull in a lot of this stuff, and I think at some point along the line, we've hit a couple ones. I think one interesting one to talk about was initial device enumeration. So when you boot these things up, we have this problem where some devices enumerate like thousands of peripherals, right? It's kind of crazy to think that internal to these embedded devices that there are 1,000 things to discover. And the idea is when you discover these things, you might want to write software that handles them. So on boot up, you get 1,000 notifications. They get filled into this database. And for people familiar with nerves, we keep track of this stuff in a component called system registry. So as we grew, things slowed down. So we had perhaps a non-optimal implementation of both device discovery and updating this database and sending messages out. We spent a lot of time working on that. And I think as pertains to this talk, one of the aspects is just going through we look at things like how can we reduce the number of events? How can we make each update less intensive? So we spent some time on, I think we're at a point right now where we're getting ready to make some bigger changes to nerves to support this use case a little bit better.
Like what? Can you share?
If Justin wants to share, I pull in.
I'll give you the problem that's trying to be solved, right? It's always with nerves. It's kind of like something that you take for granted with programming other OTP applications. And the easiest thing to talk about is the network, right? Typically, people just expect that the network's going to be up when they start a node, and it's up to you when running a nerves device to be able to configure it. But there's other dependencies that you depend on, right? That might just inherently think that the network is always available or make bad assumptions, and so you have to kind of handle those situations. And also furthermore, in handling those situations, it might be interesting for that application to somehow receive information on when the status of the connectivity of the network may change. Yeah. And so on your system, on your laptops, your system will respond to situations when the network is down versus up, because applications will receive notifications of the status of it changing. Like in Chrome, you'll get no connectivity, or you might catch the network at the time when it's just switching. It's like, oh, there's a network switch I'm detecting, and it's like sometimes it might be interesting to know who's responsible for bringing up the network in the case of a nerve system. And so that's what the point of system registry, one of the points of system registry that it was trying to be able to allow for is that anyone can contribute information about the state of services that are taking place inside of a machine, like networking, what IP addresses there are, what interfaces are configured. And then anyone else can also query that state and then operate on when it changes or becomes available or becomes unavailable. That system sort of got some gum in the works on its performance, and that's why we were trying to be able to make those optimizations. Like instead of on every single enumeration event of something getting added that could cause an event to happen, like network interface being configured versus not, instead of doing those one at a time, we'd batch them. But it's still got to the point where it seems like we need to have a more meta way of attacking this kind of solution. There's a lot of these conversations that we hear around the ecosystem these days regarding how can we satisfy this need that we have to be able to do some early boot time reconfiguration. And Elixir releases in 1.9 started to be able to touch upon this point. And so there may be some stuff on the horizon that if we just were to pull back and operate at more of a meta level like releases do, we may be able to solve some more of these problems. So we don't really have anything more to be able to share about how we plan on going that route yet, but that's kind of like the issue, like the pain that we're starting to feel in that area.
And if any of our really smart listeners heard that and think they could help, they probably should reach out.
PR is welcome.
R's and PRs.
So just to add on to this a little bit, the frustrating thing about embedded on some of these platforms is that you run something on your laptop and it just returns instantaneously. And you're like, this is taking milliseconds? And then you run it on Raspberry Pi Zero, being just picking on one board that we run on. And it takes 3 seconds. And you're just like, how can this thing magnify so much? And one of the optimizations that we did to help boot time was, how do you load quickly, right? So at boot time, we compile in embedded mode, which means that all of our Beam files are loaded at initialization. We found that to be a good thing to do for runtime performance on a lot of projects. But the consequence of doing that is you put in the power, Linux boots, Erlang goes through and loads the whole list of Beam files. And there are hundreds of them. And that's doing a lot of I/O. So, and then for nerds, we save everything on a compressed read-only file system. So it's kind of hopping around and decompressing different parts. And the Beam files are small, so they don't benefit from being loaded together. The optimization was to read the OTP initialization scripts. So OTP generates this list of Beam files in order that they get loaded, and reorder the files as they get stored in the read-only compressed file system. So the reads can go sequentially through the file system and hit them one by one. That was an improvement that you totally would never see on a PC because it's instantaneous, but you can see it on some of the slower boards.
Yeah, that actually had like a pretty decent size gain. Almost, it was like 8 to 10 seconds if I remember, but that's by far not to be the accurate quote, I would say, but I think it was a pretty decent gain just by implementing that feature.
Right, yeah. Yeah, I'd have to get out my notes again to see where it was, but it was a surprising amount for something that felt free on the PC.
Yeah, so that all happens at compile time then. It allows us to generate that compressed root file system with the correct file ordering, because at compile time we can introspect and understand what the Beam's going to do, like what its load sequence is going to be based off of being able to comprehend the boot script, because we have it at that time. So we know what order things are going to be loaded in.
That's wild. So I guess we can kind of keep moving along. And one of the questions I had was if there's ever a time where Elixir is too slow and you need to move to hardware. So like, I know FPGAs are, I think, the first step you go. Like, have either of you ever needed to do something like that?
Well, I mean, when Elixir's too slow, I usually drop the C first to see if that works. But you're right, at some point, you need to go to something hardware accelerated. So on the embedded side, a lot of the reasons to go to hardware accelerated is because a piece of hardware already exists in the chips that you're using. One that comes up a lot for me is video encoding, right? The video encoder already exists in the chip. You just have to route the data properly through the system from the camera to the H.264 encoder, for example, and then to wherever it streams. And that H.264 encoding would be crazy to do in Elixir. Well, I mean, at least it would be something that someone could try, but I suspect that it would be much slower. But getting into generic parts, I think the FPGAs, that's not something that's really hit the Elixir realm, except there is some work being done on that, and not only FPGAs. So I guess we could talk about this. Both FPGAs, GPUs would be another thing that hits more embedded devices now, and then SIMD type of instruction sets on the CPUs. So
yeah, that's actually some of the work that's coming out of the research from people in Japan. So there's a work that's being done on the GPU front that's called Pelame, and that's essentially taking that's GPU and SIMD optimization, SIMD instruction optimization. And so the idea there is that you'd essentially be able to wrap portions of your code in a block that could then be identified and converted into either optimized SIMD instruction code that can run on the CPU, or optimized code that can actually be run on the GPU with some of these routines. So that can compile it to run it in these different locations to be used then for parallelization and performance gains. And then the other side of things is the work for the FPGA stuff, and that's with the Kakatoris library, I believe. It's a means of being able to take similarly instruction sets that can get rendered down to FPGA, what is that called? Hardware specifications? Yeah.
The bit streams that you load the FPGA with. Yeah.
Yeah. And then that'll essentially configure it so that it can operate too many as it can fit in the optimization that they're looking for of that kind of code parallelization. So you can basically think of it as a flow, Erlang Elixir flow model, like Broadway and flow. It optimizes flow pipelines to be able to parallelize them with FPGA routines, like as many as you can program onto that fabric. Yeah.
And then they hook up the device driver so that you can ship the data back and forth and capture in your Elixir program. So that's pretty neat. So there's that. I guess the other thing to bring up about hardware acceleration is just the hard real-time aspect of this is that there are a set of tasks that we have on embedded projects that just have these deadlines. And that's, I guess, more the field of writing a little piece of code either in microcode or for a microcontroller. I mean, FPGA certainly, not using the cockatrace library, but just using standard FPGA development, might have some hard real-time stuff that you'd want to interface with. I think that's fairly common, at least for the nerves community. Just we don't have or at least our story for how do you handle hard real-time is to delegate it out to a microcontroller or other piece of hardware to do it. The GRISP project, they're working to make the Erlang virtual machine a better place for these hardware real-time kinds of things that you might want to do with your device. So we of course keep up with that because that's awfully neat to be able to write that stuff in Elixir or Erlang.
Yeah, I can't imagine what it would take to take Erlang, which is soft real-time, to make it hard real-time. That sounds like a lot.
Right. Yeah, well, I mean, we have to get the GRISP guys on here. They have a lot of interesting stuff to share, for sure.
All right. So I guess our next set of questions. So one thing that is always kind of interesting to learn about is as an application developer, I guess like the Joe Armstrong quote is like, make it work, make it beautiful, then make it fast, right? But you don't only really have to stop at make it beautiful. So like, because you guys are doing a framework, do you ever have to make it ugly but very fast so that it benefits like the whole framework? And if you do, what's an example of one?
Wow, this is like the trick question to make us admit to doing something really ugly, some really super ugly hack somewhere in our system.
Jose admitted it, so don't worry. Elixir has some ugly things in it so that it goes fast. So you're off the hook.
Oh, perfect. I think the nice thing about the whole majority of the code that people write for nerves is that it is not embedded stuff. It is just like we have some logic that makes sense to run located on this device, right? That's doing some kind of control or do some side of networking. It's not a piece of logic that runs well, geographically someplace else, be it for network connectivity or response time to sensors or what have you. A whole lot of that code, at least in my experience, has just worked. And I think that's kudos to Elixir. And there's that such a large body of code can run without a lot of performance tuning. Now, you do get into some of the stuff that definitely does require performance tuning. I'm not trying to get rid of that. But if you're going to ask me for like hacks that I've done or stuff like that, and I mean, I guess where I would start was where is some of the low-level communications with notifications on hardware insertions, doing some of the batching of events, scraping UDEV notifications quickly, handling, you're going to get me to say, just dish on all the tricks that we have. Why we haven't enabled some features in the nerve systems because they slowed things down for us on boot time versus. So I have to say, there's like a lot of things we could mention, but I really want to concentrate that so much of Elixir works that we don't have to fight it. And a lot of the places where I come in where I want to fix something, there's some C library or something that I can take off the shelf that has a more optimal, has performance that works for my app. And Justin's laughing here like he wants to add.
What's so funny, Justin?
No, I think what Frank is nicely trying to be able to avoid saying is that system registry kind of led itself to a path of pain. And sometimes like this is like, it's tough. Like we find ourselves often in situations where, we're a little bit at odds with the like interpretation of what is the OTP way, right? And the reason for this is because our principle is that embedded devices operate best when their OS is Erlang. Like why not? It's a great virtual machine. It's like we boot you to Erlang. Like that's what the principle is. And that's good, but that means that like the constructs that we work with inside of Erlang, like applications, for example, like we know that if you try to start up the Erlang VM and your application crashes and it doesn't start up, you come back to a prompt, right? And it's like, And it's like, but what does that mean? That like if Erlang VM was actually a system, like imagine it to be your Mac, and you start your Mac and Slack crashes, and that means your Mac can't boot. I mean, that's probably the actual side effect of Slack crashing, to be honest. But the reality is, like, that's not the desire that you'd want if you want to be able to like try to figure out why Slack crashed, or in the case of something else, like have some other code execute. It's like just having it exit felt like the wrong choice. And so like for a very long time, we found ourselves operating at this like meta layer, like the outskirts of Erlang, the VM, like right on the edge, and having these desires to try to fix some of this like pain. And so out of that, we breed some of these experiments on like, how do we manage some of this meta level? And system registry was one of those experiments. And that the very difficult part about these experiments is that it's tough to be able to think of them like you would from a standard project management perspective, where you're just like, oh yeah, we'll just A/B test this thing. It's like, no, like, what do you need? You need an entire giant, like you need this like massive system, this like piece, and you don't understand what the pitfalls are until you've gone down that path. Like there's not a lot to say about that area that you're kind of like poking around in the dark through. And it's like, and so we've reached this point where we've sort of capitalized on the results. We've captured the results of the system registry experiment. We're ready to now iterate again, which may lead us down a more focused path. So those are usually situations that that I at least personally find myself looking back on and considering hacks, because we all write hacks, right? But they're only hacks when you look. Some of them are only hacks when you look back and you're like, well, that was a bad idea.
Actually, I exclusively write hacks.
Yeah. Well, be honest too. There's hacks that up front we're just like, this is a hack. But there's other ones then there's the rest of your code that it takes a long time for you to come back and look at it that it's a hack.
Well, we have this tension. So Justin and I, we have this huge tension. So we're running on the Erlang Beam. So that's one place. But we're developing what some would consider an embedded Linux system. We use Linux kernel. We don't use all that much of the other Linux user land, but there are embedded Linux ways of solving a lot of these problems. There are Erlang OTP ways of solving these problems. I mean, sometimes we run into someone from BSD or from VxWorks who uses VxWorks, which is real-time operating system, and they have their own set of ways of solving these problems. And then the question comes up, what do we do for our platform? And I think for us, the embedded Linux versus Erlang OTP way of solving problems sometimes doesn't mesh at all, and you have to choose. And we get into these situations where the choice that favors the embedded Linux some field just backfires, and vice versa. And I think that's the past couple of years we've had to iterate based on that tension.
I'm curious if, from working through a lot of these struggles and how long have you guys been working on Nerves? For 3 years at least? So after struggling through all this, have you learned anything that would, if you were to start all over today, change the direction that you had gone in or the methods that you had chosen?
Well, we're just about ready to release a new networking stack. So I think we've captured that answer. So yes, I think we've learned continuously. And I think that we've had some, V2.0-ish things that have been passed around over the past year or so, and that are slowly making its way out to the open source community. I mean, some things that we like early on, it wasn't obvious that that running the Beam on the Linux kernel was a good move, right? That was a tough decision. It was pragmatic at the time because there wasn't drivers for some of the hardware we need to run on. But Linux has benefited us a lot, being able to run on a variety of platforms and get some random hardware working quickly. On the other hand, the networking stack, well, we had that's been a learning experience.
So while we're kind of on this subject, I'll kind of change the direction just a little bit, because we like to ask at least some functional programming questions. And I'm curious if functional programming as a paradigm, being sort of the way that we do things in Elixir land, did that influence at all what the architecture of Nerves ended up like? And could you dive into that a little bit?
So Justin's looking at me, so I will give a first pass at this question. I actually didn't come to Erlang and Elixir for the functional programming part. I came to it for OTP. OTP, when I was building embedded systems, which is my background, OTP had some very nice solutions, very elegant solutions to some problems I was having at the time. And functional programming was kind of thrust on me because it wasn't like I was getting OTP with C++ or pretty much any other language I was looking at the same time. Now, having said that, when I look back at my original Erlang and Elixir code, it may not be the most functional. And I think I've grown over the past couple of years to appreciate some of the ways.
Yeah, I came for the OTP and I stayed for the functional programming, similar setup. So we kind of we had separate path and problems that we were solving at the time. Frank, you've been working on NURBS for about almost a decade now, right? Or just under?
It hasn't been a decade. It's been a little under a decade.
A little under.
Yes.
8 or 9 years or so. Yeah, I don't know.
Something like that. I think the first presentation was.
Yeah, and so about 4 or 5 years ago, we kind of met up and started working on it together. And so before that time, though, I was also interested in the OTP aspects of it. So I was trying to be able to basically write OTP in Ruby, and I was learning Ruby at the time. So I didn't drink enough of the Kool-Aid that I stayed for the Ruby. I actually discovered Elixir during that time and started working on some stuff over there, and then we synced up on things and continued. But yeah, I remember that my very first experiences of learning functional programming, because my background was also in object-oriented languages like Objective-C. I did some C++ back in the day, and most .NET programming stuff, and so my head was definitely object-oriented. And so the very first thing I was tasked to do was to write the Microsoft SQL Server database driver for Ecto. It's really getting thrown in head first. It's okay, let's because Elixir did, we really wanted to try it out, but it was a .NET shop, and so we needed a driver for the database, and so it was all right, well, let's see what I can get running. And it took me a really long time to kind of really get the concepts of the usage of processes and gen servers and the idea that you could actually have control at that level inside of a language. But when it finally clicked and made sense, I feel since those times of truly understanding and embracing functional programming, it's been more helpful in describing certain parts of things. I believe that it's good at describing state machines. And so because of that, there being a lot of sort of state machine and state transition in embedded programming, that it helps me make better decisions for patterns on how to be able to sort of design for safety as a default, and separation. You just kind of get that as a benefit if you're doing things properly, the isolation, that safety net. And so I do believe that it helps me force me into some better decisions nowadays. And I can't imagine life back in the, I go back and I look at object-oriented code now that updates things by reference, and I'm just
yeah.
I can't. It just takes so much energy to grok that these days.
Yeah. I may also have, once we started doing Elixir, all of my Ruby started looking a lot more immutable, even though it wasn't.
Oh man, there's a lot that we could go into there, but it's definitely interesting how you come for a certain feature set and you think that you're going to sort of impose your architectural ideas, but then the paradigm actually influences you. So we've got a few minutes left here. I want to be super respectful of everyone's time. Frank, we're going to get you to a birthday party, but we want to leave you with a softball. What does not exist yet that you would love to see made with Nerves?
Right now, the thing that I most want is to see the Nerves projects that are going on behind the scenes get, a few of them have been shipped, but I want to see more of them shipped. I mean, it's just there are a bunch of features that I could talk about, but by far the icing on the cake for this has been such a long project for, I think, both of us, is to start seeing a lot of this code with Nerves being shipped in real devices. That's even more than what people hear about. I think people hear about half dozen or a dozen deployments, and there are a bunch of ones that just don't get publicized. But I'm really looking forward. I love it. I love hearing about when this stuff gets used for real, and I think that we're getting to the point in time where the development cycles for these embedded devices, which are much longer than web app, can start making it into the field and get publicized a little bit more.
Okay, so see more of what's being made behind the scenes.
Oh, I mean, people are making neat things. So
Well, to expand on that one too, I mean, people are making neat things, and for some reason they don't like. It just seems like when you're building things out of hardware, even though it's using open source tool sets, that secret sauce is like so much more special than writing a web application. I think because it's like something that's physically there. It's tough. Yeah, I want to hear the more vocal responses to that. As far as like stuff built with nerves, like I really want to be able to see nerves. Like I'm going to answer part of the question that you didn't ask, which is the future of portions of nerves. Like I really want to be able to see advancements on Nerves Hub, and I'm excited for this time coming up that we over the next year or so to try to be able to focus more resources on things like the web design components of it, and to get it to look and feel a little less clunky on the web part of it, because we're a bunch of systems engineers, putting together front end web applications. Like, yeah, I know JavaScript, yo. Yeah, so a little bit, like pushing that front a little forward a little bit more, because I think that the delivery mechanism, like if we can truly and like make that really really slick and seamless, like then like that'll speed up the development pipelines, and speeding up the development pipelines will get more products out there and more examples and use cases and more studies. I'm really excited because I think that as a community we kind of like are looking for like ways that we can like really like verticals that we can really grow in. And while the web is definitely one of those verticals, I think that focus in the one that in nerves and hardware development is a really interesting one, because we're not really presented with some of the same challenge sets that the web people are. Like when we ask people to come and run on nerves, like we're not necessarily asking them to rewrite their entire system in another language to reap benefits. We're just asking you to kind of like package it a little bit differently so that you can get access to some of the benefits, and then you can explore that path a little bit more, and then maybe use that as a means of like expanding your development team or hiring different developers and getting more use out of existing ones. And so from the perspective of things, like I'm really excited for the future of the language and the ecosystem and what we can do with promoting its use in the embedded development workspace. Because Erlang was originally designed to run on embedded boards, so
So it's a no-brainer.
Yeah, the reason that Phoenix is so good is because Erlang was designed for embedded systems.
Okay. Well, any final plugs or asks for the audience other than the ones you just made before we let you go?
No, let us know what's happening. We love this. We love it when we hear about any success story or anything with nerves. Certainly if you're having trouble, let us know that too, so we can address it. But
you heard Frank, direct all customer service requests
to Justin. Yeah, you saw it.
Oh man. Well, this has been a great episode. You two are really inspirational folks, really smart developers. Really glad that we got to have this conversation today. Justin Schneck, Frank Hunleth, thank you so much for joining us today on Elixir Wizards.
Oh, thank you, Justice Eric. It's so great to hang out with you and see you guys every time at conferences. You're definitely everywhere. It's pretty good.
Thank you. Thank you for joining us, man. And it's good to see you guys at conferences as well, for more substantive reasons than just the fact that we're everywhere. But once again, this has been Elixir Wizards with Smart Logic, talking about working with Elixir. Justin Schneck, Frank Hunleth. My name is Justice Epen. I'm joined by my co-host, Eric Ostrich. This has been Elixir Wizards. See you next time.